All right, welcome back to Hot Topics. This topic, absolute value equations, we realize there's about 3 or 4 topics related to absolute value equations in ALEKS. And what we're trying to do here is summarize them for you so that you kind of get a clearer picture of exactly what you've just gone through. Or for some of you, it might be helpful to watch this first and then go into ALEKS and solve all those equations.
Right, because there's quite a wide variety of absolute value equations in ALEKS. So even if you've had this topic before previously, you may not have seen all of the types of absolute value equations that ALEKS is going to throw at you.
Let's get right into it. The basic equations with absolute value look like this. Now, we just threw these out here just to kind of give you a big picture understanding. Normally when I introduce this in a class, I ask students, the absolute value of what number or numbers equals 10? And after a little bit of thought, most students realize that x can equal a positive 10 or a negative 10.
Because remember, that's what absolute value does. It makes things that are negative positive. It actually just measures distance. It measures the distance from 0. So the absolute value of positive 10 is 10 because from 0 to 10 is 10 steps. And the absolute value of negative 10 is 10 because from 0 to negative 10 is also 10 steps. But most students find it just easier to remember that absolute value makes things positive. That's what it does.
That's it. So now, when you look at the second problem, we have the absolute value of x equals negative 10. Now, can an absolute value ever equal a negative number? Not in this course, and not in anything that we teach.
Yeah, absolute values can't be negative.
So there is no solution to this, and in ALEKS, you will probably see this symbol if there is no solution. This is the empty set symbol, or the no solution symbol, I should say.
Right, exactly. ALEKS uses this just as a way to represent the words there's no solution. The set for this solution is empty. So anyway, when you see that, that's how you tell ALEKS there's no solution, that symbol.
Okay. These next two look more like what you're used to seeing in ALEKS. Here's an equal to sign, and again, I use 10 specifically for this problem. Students see this and they go, oh my goodness, what do I do? Well, remember, all we're trying to figure out is what value of x makes all this in here either equal to 10 or negative 10.
Right, because if I hit it with the absolute value sign after it equals 10 or negative 10, the answer is going to be 10, which is what I want.
So we're going to set up 2 equations. Equation 1 is the original, 2x minus 4 equals 10. Equation 2 is 2x minus 4 equals negative 10.
So almost every absolute value equation is really just 2 equations in disguise. If you solve the 2 equations that are disguised, you'll have the answers to the original equation.
Exactly right. So to finish this, we realize you've solved enough equations so far, so you're going to add the 4, and over here you're going to add the 4. So that gives you 2x equals 14. And then over here you're going to get 2x equals negative 6. Then your last step, divide by 2 on both of these. Whoops, forgot the 2 there. There we go. And then your final answers. X equals 7, x equals negative 3. Both of those are the solutions to that one equation. So make sure you insert both of those into the answer palette there in ALEKS.
Right, and just to take a second, if you plug 7 in there, you get 7 times 2 is 14, minus 4 is 10, and certainly the absolute value of positive 10 is 10. If you plug negative 3 in there, negative 3 times 2 is negative 6, minus 4 is negative 10, but the absolute value of negative 10 is also positive 10. So both of those answers work. They do what they're supposed to do.
That's it. I didn't mean to put a negative there, but just reiterating what Bill showed you. When you
I
hit
talk
negative
really
10,
fast. It's hard to write as fast as I talk.
When the negative 10 in here comes out, it's positive. Then, of course, over here, this is 14 minus 4, which is 10, and we know the absolute value of that is 10.
Right.
So there is a simple way to check your work. Feel free to do it, especially when you take a test. Take that time to check. Now, this next one, you'll notice we have something in front of our absolute value. It's a 2. Now, you might say, well, do I just write out 2 equations? No. You want to get used to isolating the absolute value before you do anything.
Right, so you can't rewrite it into 2 equations until you have the absolute value sign by itself on one side and a number on the other side. You got to do that first.
That's it. So now we've reduced this down to just x minus 4 equals 5. Now we're ready to write our two equations. The first one is always the original. The second one is the left side equal to the opposite of the right side. Now, to solve this, I'm not going to write anything because I think everyone watching knows you're going to add 4, and that's going to give you 9. Then over here, when you add 4, you're going to get -1. Those are your two solutions, and you are finished with that one.
And again, you could go ahead and check in there, and you'll see that those solutions do work in the original equation.
That's it.
All right, next.
Okay, these next two involve a new symbol. The first 4 we've done involved an equal to sign. These involve less than signs. Now that's what you want to start focusing in on, is the sign that you start with, because that determines the look and how you want to set these up.
Right, the way you rewrite these problems depends on whether it's less than, or equal to, or greater than, or equal to. So first, we'll look at how to set up problems that involve either less than, or equal to.
That's it. Now, this first one, when you have a less than, rewrite the original problem and then put greater than -5. Now, it looks like a less than. -5 is less than this, but when you read it from left to right, it's -5 is less than this and less than 5.
Or another way to think about this is if there's a less than sign in an absolute value, what we're doing is we're centering whatever the expression is between the two possible values, the two possible numbers whose absolute value equals 5, that is -5 and 5. So anytime you have a problem involving less than or equal to, you can rewrite it as this single inequality with the expression in the middle and the numbers on the ends that represent the two values that give you, in this case, an absolute value equal to 5.
Yes, and we call this a compound inequality.
Right.
And at this point, you've already solved those, and we know you know how to solve them. But again, just in case, if you've forgotten, we will go through the steps. Step 1, to isolate x in the middle, the first thing you want to do is add 7 to all parts.
Right, so in all 3 places, and in these problems, instead of just having 2 sides to the equation, there's essentially 3 places. So make sure you add 7 in all 3 places, not just in the middle and on the right.
That's it. So -5 plus 7 is 2, is less than 4x, is less than 12. Now your last step, again, you're trying to isolate x, so you want to divide by 4. So that gives you 2/4 is a half, is less than x, which is less than 3. Now, just to be sure you've done this right, what is an easy number between a half and 3? 1. Take the number 1 and make sure it satisfies this equation. If it doesn't, then you probably set this thing up completely wrong or you had an error somewhere in your computations. This is not a foolproof check. This is just a quick little check to make sure that you don't have something obviously wrong here. So, plugging in 1 in the original problem, you get 4 times 1, take away 7 is less than 5. Well, 4 times 1 is 4, and 4 minus 7 is -3. Is the absolute value of 3 less than 5? Yes, it is.
Yeah, the absolute value of -3 is less than 5
3.
because
Yes.
3 is less than 5. So again, as Jerry said, this is not a foolproof method of checking, but it's a pretty good hint. If the number that you check comes out correct, then you should feel safe and go on to the next problem.
That's it. So let's look at this next one. This next one is similar to that other situation where we have a coefficient out in front of the absolute value. So remember, when you're thinking about the first step in all these, the first step is always isolate the absolute value. So we're going to do that on this problem by dividing both sides by 5. Okay, so dividing by 5 gives us the absolute value of -x plus 2 is less than or equal to 6/5. And Bill?
Yeah, let's just change this to a decimal. Again, you're allowed to use decimals, and that'll make the numbers a little easier to work with. So let's use a decimal this time. That's 1.2.
1.2. All right, now we can rewrite this problem. The new equation is going to be -x plus 2 is less than or equal to 1.2. And then on the left side is greater than or equal to -1.2. Now, to solve this, all we need to do is subtract 2 from all sides. And when you look at -1.2, look at that as -$1.20. We're
Right.
trying to do these in your head. So, On this side, we get negative 3.2, and the middle is negative x. And on the right-hand side, less than or equal to negative 0.8.
Right. $1.20 minus $2 would mean you're behind by 80 cents.
Yeah,
All right.
rough life. Now, your last step is to get rid of that negative on the x. Now, a lot of students just like to ignore it and say, oh, I'm finished.
Right.
Well,
remember, we don't care what negative x is. We want to know what x is.
That's it. So we're going to divide each term by negative 1.
But since you're dividing by a negative number, Jerry, what do they have to do?
They better flip those inequality signs around. Matter of fact, you ought to just do that first.
That's good advice.
And then over here, that's going to become positive 3.2. And over here, that's going to become positive 0.8.
And notice that if you didn't flip the sign, the numbers you have there wouldn't make sense. You'd basically be saying x is greater than 3.2 and less than 0.8, and there are no numbers that are both bigger than 3.2 while at the same time being smaller than 0.8. Once you flip the signs, it now makes sense. This says we're looking for numbers that are larger than 0.8 but smaller than 3.2. Hopefully that might help.
As a matter of fact, you might not like how that looks, and normally it's probably more appropriate to flip this around and write it this way. And I know this drives some students crazy, but these two things mean the same thing.
Right. Again, we're essentially just reading it going in this direction rather than reading it in this direction because we always want the smaller number to be on the left and the larger number to be on the right. So if the problem you have has the larger number on the right and the smaller number on the left, then you want to flip it around. I hope I said that correctly.
Exactly. And in interval notation, this is more appropriate. The 0.8 has to be on the left and the 3.2 has to be on the right, and they're both brackets because of the equal to sign. So anyway, over here, just to showcase this one in interval notation, this one would have parentheses because there's no equal to signs in the problem. Not all of you may have watched that Hot Topic video on interval notation.
Right, so that if there's no equal sign, we use parentheses. If there is an equal sign, we use brackets.
Okay, let's move on.
All right, let's move on.
This next one involves a greater than symbol. Now this one, you will set up two separate equations. Only the less than will you set up the compound inequality. When you have greater than symbols and equal to, you're going to set up two separate equations. So this one, you're going to have 3x plus 5 is greater than or equal to 4. And we always use the term or. And then 3x plus 5 is less than or equal to negative 4.
Right, so the greater than or equal to sign goes with the positive version of the number. The less than or equal to sign goes with the negative version of the number. That may be helpful for remembering purposes.
That's it. Now, again, we're going to assume solving equations is a non-issue here. It's all about setting these up. Once you have them set up, it's hard to get these wrong. You move 5 over, obviously it becomes negative, so that's going to give you a negative 1. Over here, when you subtract 5 from both sides, you get negative 9. And then dividing both sides by 3 on each equation, you get negative 1/3. And then over here, you get negative 3. Now, again, if Alex asks for this problem to be answered in interval notation, it'll look something like this. You actually have two parts, and you'll have to use the union symbol. Let's start with the less than part, because this goes to negative infinity. So you'll have negative infinity to negative 3, and negative 3 is included, so that's a bracket. Then you're going to union that, with negative 1/3 to positive infinity.
Right, and if you aren't clear on how to do the interval notation here, if you go back to our previous Hot Topics on inequalities, I actually draw some number lines and show where these come from. Again, the way these answers are, although most students don't realize it, when you're writing things in interval notation, you're actually representing the solution as a set. And we don't add sets together, we union them. So to say that all of the numbers in both of these sets work as solutions to the original inequality, we use the union symbol to represent that. In your mind, you can think of the union symbol as just a way to say and. It's just a way to say this set and also this set will work.
I think your better term is or.
I know. The technical term is that a union symbol corresponds to or. But in your head, you can think of it the other way around, because
That's
it
right.
basically says both of these sets contain the numbers that work in the original equation.
All right, this next problem over here, you'll notice that the absolute value part is not isolated. Matter of fact, we have two pieces to it that are on the left-hand side. So to start this problem, you're first going to add 4 to both sides, which will give you the equation 2, absolute value of x plus 3 is greater than 6, and then divide both sides by 2. So now you have x plus 3 is greater than 3.
And now it's safe to go ahead and rewrite it in terms of the other two equations.
That's it. So here's equation 1, x plus 3 is greater than 3. Notice the original is rewritten, and then the opposite of that, x plus 3 is less than negative 3. Now these are two very simple equations to solve by subtracting 3 to both sides. This one's going to give you a 0. And subtracting 3 here, you get x is less than negative 6. So you have this or this, and again in interval notation, you notice we do not have equal to signs, so we are going to use parentheses. So start with the one on the left, negative infinity to negative 6, parenthesis, union symbol, 0, comma, positive infinity.
And again, we use the parentheses because there were no equal to signs here. We used the brackets in the first problem because there was.
Okay. All right, these last three all fall under what we call special cases with absolute values. If you recall those first two problems we did, the second one had the absolute value equal to a negative 10. And we said, be careful, there is no solution to that. Well, do you notice that we have two negatives here, and over here we have a 0. Now again, think about the definition of absolute value. It's the distance from 0 to a number. Can an absolute value ever be less than a negative? In other words, can it equal negative 3, negative 4, negative 5? Can it?
No, it can't. So if you have a problem that asks you to find some way to make the absolute value of any expression be smaller than a negative number, you're just not going to be able to do it. So this particular inequality has no solution.
No solution.
And again, that Alex represents that using that symbol for the empty set.
Now, in the second one, you say the absolute value greater than or equal to a negative. That means it could equal, now I'm going to write negative 1. We know it can't equal negative 1, but think about all the numbers that follow. And I'm not writing all the decimals either. The question here is, Bill, does an absolute value, is it always greater than a negative?
Right. In other words, the idea here is we know the absolute value of 3x plus 1, whatever value of x you plug in there, will always either equal 0 or some number bigger than 0. And all of those numbers are already greater than or equal to negative 2. So here we essentially have the opposite of what we had in the previous problem. Here, any number you plug in for x will make this inequality true. So in words, we say the answer to this is all real numbers. But in interval notation,
Go ahead, Bill.
okay, sorry. In interval notation, we write it as in a parenthesis from negative infinity to positive infinity. Basically, that says any number on the number line will work. Any number all the way from negative infinity to positive infinity will make that inequality a true sentence.
That's it. Now the last one's even more thought-provoking.
It's very tricky.
We know that there are no absolute values less than 0, because that would mean a negative. But you notice that equal to sign. Can an absolute value equal 0?
And the answer is yes, it can, because the absolute value of 0 is 0. So
That's it.
if they give you an equation asking you to find the absolute value of some expression is less than or equal to 0, the only value of x that will be a solution to that inequality is the value that Jerry's written right there, that makes the expression on the inside exactly equal to 0. So basically, the original inequality is identical to actually that single equation, 5x minus 10 equals 0, and that's easy to solve.
Easy to solve. Add 10 to the other side, it becomes positive. Divide by 5, you get a 2. So this is actually the only problem we've discussed. It only has one solution.
Right, even though it's an inequality, there's only a single number that makes it true. these pretty much are the three special cases you'll see. So again, pay attention to when it's less than or equal to, when it's greater than or equal to, and if you see an absolute value equation involving 0, it's always a special case.
Okay, to summarize everything that you've learned so far, we've created this little slide of reminders. The first thing we always want you to do is isolate the absolute value sign. If there's a coefficient in front or if there's something dangling off the back, move it to the other side first. You do not want to rewrite anything or make any assumptions about negatives until you've moved everything over.
Right, so once you have the absolute value of something and a number over here, it's safe to go ahead and rewrite it in whatever form is correct. But if you don't have an absolute value of something by itself on the left side and a number over here, then you got to fiddle with it before you go any further.
That's it. And then secondly, once you've isolated the absolute value, you're looking on that right-hand side and asking yourself, do I have a negative? If you have a negative, look back at our three special cases. Remember, less than a negative is no solution. Greater than a negative is all real numbers. But if we throw in the 0 or something, like a 0,
right,
then you need to really think about it.
Right, yeah. So those again, those are quite tricky problems. But as you see them over and over, which you will in Alex, because Alex keeps them popping up, after a while, I think they'll click, and you'll find that you can do them without too much trouble.
Yeah, and once you've gone through those two mental steps, the last step is solve. And if you'll notice there on your slide, it says if you have two greater than symbols or equal to signs, that's when you're going to separate and write two separate equations. If you have less than, you're going to write one compound inequality. And we cannot make it any easier than that.
Right. Hopefully this cleared up any problems you had with it. In the book, if you want to look for more about this, where is this in the book, Jerry?
You'll find it in Chapter 1, Section 8, which is roughly the pages 57 to 60. So look around in there, and that's where you'll find some more examples.
All right. Whew, this was a very long, hot topic. Hopefully the next one you look at won't be quite so long. Take care.